to compute the arc length, do you guys remember the arc length? You had A to B r prime of t dt, arc length. Remember this? Then what did I do next? FDS, which was what? A to B, I put an F next to it. This was section what? 13.3. This was 16.2. And then I did F as in it has a density. Then what do I do? Very quickly, I followed it by this, which was F dot, r prime of t dt. And this gave me, this was the scalar line, vector line, and arc length. Now, equivalently, what would be equivalent to arc length when I talk about surface? Who said surface area? Whoever said surface area, a brownie point. So now, take that surface area formula, stick a scalar function in it. What would you call that? What would you call if I stick a scalar function? Scalar what? Surface integral. And if I dot with a vector function, what would you call that? Vector surface integral. So the entire discussion from now on is to match the surface integrals with those line integrals. Now, we discussed this last time. I'm writing it down. What was the parameterization? Parameterization would take us, I'm doing a quick review. Parameterization, let's say G, take us from a parameter space, U and V, into a three-dimension, X, Y, Z. So it takes little region in here, let's say this grid line, take it to a surface with this grid line. Every little delta X times delta U, delta V in here, delta U, delta V, is going to be stretched out exactly the same way that we got it stretched out in transformations. What was the stretching factor there? Delta U would become delta U G sub U at the point, right? And then delta V becomes delta V G sub V at the point. Agreed? And then we cross them to get a vector that contained the area, the new area, right? So when you cross them, it's a vector whose magnitude is the new area. So if I take the magnitude of that, what do I get? I get delta U, delta V, magnitude G sub U cross G sub V. This gives me the scaling factor. So if I integrate on U and V, right, I still need to have that scaling factor work out. Agreed? So what happens is that I basically, when I integrate to find surface area, integrate over du and dv. So dA of u and v, and it has to be a double integral because it's a surface integral. But I can't do one in here, can I? What do I need? I need that rescaling factor, that Jacobian sort of thing. Fair game? So I still need G sub U cross G sub V. That's it. That's the last thing that I said last time. Almost. Oh. This is D of U and V. So that's the last thing that I said. That's the golden formula. Golden formula in pink. And I don't have gold. So golden formula over there, I just had you a formula for surface area. Now I'm going to use the formula for surface area very quickly. One quick thing. When I say G of U and V, how many are in here? How many components? X of U and V, Y of U and V, Z of U and V. When I'm saying G sub U, what do I mean? Partial of X with respect to U, partial of Y with respect to U, partial of Z with respect to U. Agreed? And then when I see G sub V, I mean X with Y sub V and Z sub V. Any ambiguity at this point? Are we good? Example time? We're ready? We can do this. Do not get sick. That's an order. Work on it. So stay healthy, sleep well, do stuff. So here's the formula, golden formula area of S, surface S, parameterized with what? G. If I want to find the surface area, I use this formula. Surface S parameterized by G. Now let's try to find the surface area of a sphere of radius R. We always start with little and then make it bigger. So surface area of, first of all, do I have a parameterization? What is your suggested parameterization for this, my friends? Spherical, somebody said spherical. Am I supposed to use rho cosine theta sine phi, rho sine theta sine phi, and rho cosine phi? Wait, how many parameters here? Three allowed in here or not? No, so how many of them are changing? How many of them I can get rid of? I can get rid of one of them. Which one? Rho. What is rho? R, constant R. R is constant. Right? So what are the two other ones? Theta and phi. Do you see that? I put the parameter inside of G. So now I have R cosine theta sine phi, R sine theta sine phi, R cosine phi. Now, that's the step one. What is the step two? Find that and that so I can find the value inside the formula. So I'm doing G sub U. What is U? Theta. So G sub theta is going to be negative R sine theta sine phi, R cosine theta sine phi, and what's the last one? 0. Now G sub V. Oh, G sub V, phi. So this one is going to be R cosine theta cosine phi, R sine theta sine phi, negative R sine phi. Step 3, cross them together. right? You've done this multiple times. It's ugly, right? Do you remember what happens? I will have an r squared sine of phi, correct? And then what else is left? As I'm crossing, I'm looking at this. I get negative r squared sine squared phi. So what is left is sine of phi cosine theta, negative of that, right? This. And then the second component is going to be minus sine phi sine theta. And then I will end up with the last component is going to be negative cosine of phi. Okay. Why did I do it this way? Because I wanted to remind you, you computed this. What is the magnitude of this? Without computing, what is the magnitude of this? You've done this. Go back. Bring all the files. Is that SpongeBob code? Bring all the files. You've done this. What is the answer to this? Yes. It's exactly equal to r squared sine of phi. I don't know what that is. I just like, Luke, go on. This? This one?
Yeah, it should be r theta cosine. The y.
Y? Yeah. Oh, yeah. Thank you. Sorry about that. Let me change the color. But I know what the answer is. It's the Jacobian. It's r squared sine of phi. And you guys know, okay, so here's the other trick. Here's the other trick. I know if I cross these two together, I'm going to get a normal to the surface. A normal to the surface. The magnitude of that normal is r squared sine of phi. Then I put in this randomly. But this looks familiar. What does this look like? This is the unit normal inward. Unit, you computed this multiple times for midterm 1. Unit normal inward. Unit normal inward. So I looked at that and I saw there's a negative sign. I figured out it has to be the unit normal, but is it outward or inward? It's inward. That's all I did. So I did this so far. I really didn't need to compute that. I just needed to remember Jacobian. All I needed to remember. So would you guys not forget this? Because unit normal looks like the unit circle parameterization. Unit normal looks like a unit circle parameterization for sphere. Unit circle, not circle, the other one, unit sphere parameterization. Now that I have this, the next thing that I want to do is to compute double integral on the region. And I did something very stupid. What is this stupid thing that I did? When I parameterized, I didn't give you parameter bounds. What are the parameter bounds? What are the parameters? Phi equal between pi and 0. Now, those parameter bounds are going to be the bounds for D. D is the region for parameters. It's the left region that you used to have for transformations, right? So now I have integral from 0 to 2 pi d theta d phi. And I have 0 to 2 pi Yeah, it sounds weird, 0 to pi. And so now the theta, r squared and sine of phi are both constant in terms of theta. So I get 0 to pi, and r squared sine of phi, theta 0 to 2 pi, which is 2 pi. 2 pi, and r squared is constant, comes out. And so it's going to be negative cosine of phi, 0 to pi, times 2 pi r squared. The entire thing is 4 pi r squared. That is the surface area of the sphere. My S's are more raspy when I'm sucking on my cough medicine. No one? But I thought that was funny. Sorry, guys, I messed up. Let's see if I can fit both of them in here. Can you see this? Yes or no? No? Better? Okay. So, that said, there is some points into basically by the way, you guys probably knew that formula. You didn't need to. But we computed it, basically. So the next thing that I want to say is, what if I'm trying to find the surface area of what? Graph of a function. What do I do? Can anybody remind me how to parameterize graph of a function z equal to f of x and y? G of x and y, two parameters, x, y. Don't mistake this. X and y are still parameters because I'm parameterizing it. And then f of x and y. Right? Now, according to this story, I need to find g sub u. What is u? Which is 1, 0. And f sub x of x and y. And then g sub v, which is y, which is 0, 1, f sub y of x and y. Then what do I need to do? Cross them together to get the Jacobian. Okay, so it's not officially Jacobian, but it's Jacobian in a way. We don't define Jacobian generally. We just define it for spaces from R2 to R2 and R3 to R3. But this is in a way a Jacobian. I cannot set up all this story for you, basically. So that's what it is. So to find that, what do I get? I'll put the I and J in here, JK in here, so I do that quickly. And I get what? Negative f sub x, and then I get negative f sub y, then I get 1. Magnitude of g sub x cross g sub y is f sub x to power 2, f sub y to power 2 plus 1. Agreed? So the surface area is a double integral d as the domain of the function, because domain of the function and the domain of the parameters are the same. Because we parameterize with x and y. And then you have x sub squared, fy sub squared plus 1 dA. Fair game? Okay. Time to do an example? Okay. You're still with me? Thank you. Okay. So next one. Is this a function? It is a function. So we're trying to find what is the domain for this function? Domain is unit disk. So it's not a natural domain. It's a domain enforced by the problem. Problem says only over the unit disk. Right? It's not a natural one that I compute, but it's enforced. So now what do? I find, first of all, g in here is what? G of x and y equal to x, y, and x times y. Agreed? It's exactly the same thing as that. See, z equal to f of x and y. Agreed? So here, f of x and y is x times y. Agreed? Now that I have this, I compute g sub x, and then I compute g sub y, or I use that formula. Either one is okay. And then I do the cross. So this was step 1. Step 2, cross them. And when I cross them, I know what I get over there. I get negative y, negative x, and 1. Agreed? And then I do step 3. Square root of y squared plus x squared plus 1 is the magnitude. And integrate over the region. Region is the unit disk. Ha-ha! Wasn't that the Jacobian? It was sort of a Jacobian, right? Do you agree? Now guess what? I'm going to do another Jacobian because this is the setup. What I did, I found what integral I need to integrate. This is the integral I need to integrate. But this integral is over unit disk. Who lets you do over unit disk without transformation? No one, I tell you, no one. You see unit disk, what do, Andrew? Unit disk, you transform to what? To, in this case, is the polar. It's double integral. So do the transformation to polar. Now, what do I do to do transformation to polar? What would x squared plus y squared plus 1 become? R squared plus 1. What do I need to not forget? It starts with J, Jacobian. And then dr d theta. So that's the integrand converted. That's the Jacobian. Integrand, Jacobian. And then because it's a unit disk, r goes from 0 to 1, and theta goes 0 to 2 pi. Do you guys know how to compute this? U substitution, u equal to what? R squared plus 1, du equal to 2r dr. Then so this becomes, wait, one more thing though. If r is equal to 0, u is equal to 1, R equal to 1, U is equal to 2. So let me put this out here. So that converts this to integral from 1 to 2 of square root of u 1/2 of a square root of u du. Agreed? 0 to 2 pi d theta. And then you compute. After that, I think it's easy enough. I mean, I could just look it up and say it's 2 pi divided by 2 u to power 3/2 times 2/3, 1 to 2, which is 2 pi third. For your completion. Everybody agrees so far? You guys are waiting for this? Give me a minute, I'll bring a iClicker soon. Huh? A few minutes. Give me 5. 5, I think it's accurate. Almost accurate. It's Gila's 5. Okay. My friends, I went over this. Look at what do I have here. What do I have here? I say scalar surface integral. That should have been What was this, my friends? What was this integral? What was this? Surface area. If I stick a surface function in here, what do I get? I get a scalar surface integral. So you weight, basically, you put the weight into each piece of the surface. You put, what's that called? Density. So you take each, this thing gives you, may I? This thing gives you area element, surface area element. Multiply surface area element by a density and integrate. What do you get? Total of whatever that density was. Fair game? Give me the density of something. What do you guys like as density? Huh? Charge density. So if I have F is the charge density, and this is the small area, multiply the charge density by the small surface area, and then sum it up, you get the entire charge. And that is called the scalar surface integral. Are you guys with me? Can I do one? Hold on. You may actually get lucky at the very next slide. There you go. And I'm not coming to the crowd. I am sorry. I'm trying to contain myself to the filtered area. What the? Almost. I knew I have to reuse one of the words. Are we good? Wait. What is this parameterization for? Sphere of radius what? C. So what's the Jacobian of spherical? It's rho squared sine of phi, right? What is rho on the surface of the sphere? C is on the surface of the sphere. Rho is C. So which one is the answer? E? Is that it? 4, 3, 2, 1, 0. Okay, so my turn to do one problem for you. One reason that I made you do that is because I do not want to compute G sub U cross G sub V every time. If it's a spherical parameterization, I do not want to do that every time. It's wrong. It's just not worth doing. So my friends, what is a parameterization for? First of all, when I'm computing this, what is this equal to? Oh, darn it. Let's go back. I forgot the notation. This is the scalar surface integral. The notation for this is F capital D capital S. F capital D capital S. And then when you have the vector surface integral, S will have a vector on top of it. Over the surface S. So when they give me this, see ds is like surface integral. ds means surface integral. So when they give me this, what are they asking me to do? Compute x parameterized at g. Basically, you want to find f of g, and then multiply that by g sub u cross g sub v over d. Okay. So step one, my friends. Do you have a parameterization? G. What parameters, my friends? What is the surface? Sphere with radius 3. What should I use to parameterize it? Spherical coordinates. What are in spherical coordinates? How many of the parameters I'm going to use? To which two? Not R. R is constant. Okay. And then 3 cosine theta sine phi. 3 sine theta sine phi. What's the last one? Step 2, G sub U, G sub V. It's a trick question. Step 2, G sub U, G sub V. No? Use the Jacobian directly instead. So I'm going to skip what? Because I know it. That's supposed to be know it. So it's going to be G sub theta cross G sub phi. Magnitude of that is equal to what? Rho squared sine phi. Agreed? Now, there is a step 3. Why did if I knew this, why did I bother with the parameterization? Who knows why I bothered with the parameterization? Because I knew this. Why do I need to write that? I have to, thank you, Abraham. I had to plug in the parameterization back into my integrand. What is your integrand? Step 3, compute f of g. X squared is the f of x and y and z is x squared. So f of g is going to be, this one is x. 3 times cosine theta sine of phi to power 2. Agreed? Okay, now integrate. What did I not do, was not very smart? Phi is between 0 and pi, 0 and 2 pi. Agreed? Okay. So far we're okay. Let's set this up. So it's going to be integral from 0 to pi, 0 to 2 pi, d phi d theta, agreed? And then I have 9 cosine squared theta sine squared phi times Jacobian, which is 9 sine phi. Now we're going to cry a little bit, but we're going to compute this. Just a tiny bit, just a tiny bit. But we can do this, we can do this. So now what do? Let's put all the phis, and this is separable. I can write it as 0 to 2 pi. 9 and 9 come out as 81. And then I have cosine squared theta d theta, 0 to pi, yeah, sine cube phi d phi. Much better. That one is this formula. 0 to 2 pi, 1 plus cosine of 2 theta divided by 2 d theta. The other one is this formula. Sine of phi, 1 minus cosine squared phi d phi. Why did I write it that way? Because that's the only way I have to basically make it into a U substitution. What U substitution? U equal to cosine of phi, du equal to negative sine of phi d phi. If phi is equal to 0, u is equal to 1, phi equal to pi, u equal to negative 1. So this part of the integral is going to be, this one is going to be what? Just AD1, and I know cosine of 2 theta over 0 to 2 pi is going to be 0. Therefore, it's just pi. This part of the integral is going to become negative 1 to negative 1, 1 minus u squared du. And I lost interest at this point. Yeah, then you can compute the rest of it. What? I think so, I think so. Yes.
So what did you do in your head to not
This one? Oh yeah, the part that I did in my head was that, hey, cosine of 2 theta between 0 to 2 pi is under the x-axis and above the x-axis the same amount. So that's out. That's the part that I out, and then I kept the rest. Yeah, that's the. So can I talk about this very briefly? I'm not going to do the entire problem. this problem is kind of special because you see that so far all my bounds were constant, but it is not true that all bounds are constant. For this specific case, you can see that the bounds are not going to be constant because you have this surface and the region is right down there. And so your u and v are x and y. And x and y, the bounds for x and y are not constant. For example, if I'm setting this one up, I'm going to end up with, how should I set up this region? Give it, everybody drop down, give me 5 push-ups. No, 5 push-ups in mathematics. not the actual push-ups. So what is this? How do I set this up? It's exactly whatever you have inside, which is going to be that square root of something, something. And then you have the y and z to plug in. So you have a bunch of things. But setting it up, I'm going to go, let's say, y simple, and I go from 0 to 6 minus x, and 0 to 6. Whatever comes from here and here. I just want to say that it's not true that it's always constant, the bounds. I click a time. You guys are, I had more than this. What happened? Let's do this because I have story to tell. It's math stories, sorry. The push-ups are math push-ups. Math push-up is you work your brain muscles. Hey, aren't you guys engineers? I don't know about the physical push-ups either. What's that? If it depends on your grade depends on it, you do it. Oh, okay, I'll think about it. What's that? No. Are we doing okay? I could wear my mask and come upstairs. If you have questions, let me know. So what are you doing cylindrical? So what are you expecting to happen in here, in cylindrical? You have to have a Jacobian, but look at this. This is the surface element. So you have to tell me what are the 2 parameters also. What are the 2 parameters? Z and theta, right? So the Z and theta should show up. dz and d theta. So which one? Which one? Hold on. We're just doing area element. So I just need the Jacobian. What is the Jacobian? Everybody, Jacobian is? What are d parameter? C times dz d theta. Yeah. Yes. Run. No, I know that you have the physics, but if you don't have the physics, please watch the rest. Watch the rest. I'm putting it up on the... Okay, my friends, now that our physics group is gone, nerds. You're good nerds. Sorry. I said they're good nerds. I am a nerd.
Trying to cover your tracks now.
No, wait a minute. When are we not a nerd? Is a nerd is a bad thing these days? I thought we changed that.
It's not like a good thing.
Could there be anyone more nerdy than I am?
Yes. Bill Nye the Science Guy.
No. Like, have you talked to me? No, not yet. Okay. So here's the story. First of all, I'm going to skip a few things, but we get back to it on Friday if we had time, not on Monday. My story is, I am going to try to tell you that the vector surface integral is all about how things get out of a surface. Imagine you have a flow running, right? You have this thing, and some flow is going into it. Now, do a cross section in here. The cross section is a surface, right? It's one of the applications, right, for surface integral. You have a cross section in here, and I kind of want to know how much things are getting out through that cross section. So one of the reasons that you're trying the surface integral is to basically compute that. As I'm saying, I have a direction, right? Because there might be some backflow in there also. But I want this direction. So we talk about orientable surfaces. Surfaces that can have one direction continuously all around. That's when this thing comes about. Do you guys want this? Wash your hands after it, because I touched it. But here, I'm going to give one if you guys, anybody who takes it. No? No? Okay, great. So, I should have put my mask on. Here you go. No? There you go. No? There you go. No, I didn't cough on them. I just like, it's the season for washing hands. So when you have something like this, it's not orientable. There is no direction of going in or out. Take your pen, just go about it, and see that you end up in the opposite direction. See, when you go like this, it comes out, now I'm in this way. Before I was inside, I thought. There was no inside. Now I'm inside again. So that's the story. What's that? That is one surface. This is called Mobius strip. So in here, not only I need the Jacobian, I actually need that unit normal vector. So when I compute the G sub U cross G sub V, depending on if that's the orientation I want or not, I'm going to keep it and name it N. Either multiply it by negative sign or not, and keep it and name it N. Bye, guys. Is that it? Okay, bye. I'll see you on Friday. Bye. Hey, let me put my mask on. Okay, what's up?